as we've learned in 9.5, we learned the alternating series test. Well, this is about the alternating series remainder. We can only find the sum of a geometric series and a telescoping series, we've learned. But an alternating series, we can narrow down the sum pretty good, pretty close to it. So it turns out as many terms as we want to add, the more terms, the closer we're going to get to the sum, of course. But let's say I found the sum of 22 terms. The accuracy that we're at is the whatever the next term is. So the 23rd term is how close we are. So whatever that fraction is, that's our error, that's our remainder, how close we are to the answer. So it's kind of neat, and I'll kind of show you why that works in just a second. So we can find an approximate sum of an alternating series. The remainder, the error from the actual sum is less than or equal to the first neglected term. So again, if I find the sum of 22 terms, the first term I neglected to use was the 23rd term. That's what they mean by that. So this is it in fancy notation here, but I need you to understand the notation. An S means sum of all terms. That's why it doesn't have a little subscripts. It means sum. Give me the actual sum of everything. Sum of n is the sum of a certain number of terms. So again, if I'm using my 22 example, the actual sum minus the sum of 22. In other words, what's the difference between the 22 that you added up and the actual answer is equal to what they refer to as the remainder, and that is less than or equal to the next term. So our technically, if this was gone, our actual difference is less than or equal to the next term, okay? So let's go ahead and find the sum of a 6, okay? So this is an alternating series with n factorial on the bottom, and it says start with 1. All right, so if I plug in 1, I get 1. I get a positive 1 on top, and I get 1 factorial, which is 1. All right, then the next term is going to be minus, because when I plug in 2, it'll be negative 1 cubed, so minus 2 factorial, 1 over 2 factorial, so minus 1 half. Then I plug in 3, I get a positive again, because remember it's alternating series, positive 3 factorial, 1 over 3 factorial, 1/6, minus 1, and then I'm going to have 24, 1 over 120, minus 1 over 720. Okay, that's just 2 factorial, 3 factorial, 4, 5, 6. That's what's happening. So there's your 6 terms. You're like, okay, well, if I add those together, I've done it already. In decimal, that's I have it down 631,944. All right. So that's the sum of the first 6 terms. Now there's infinite number of terms. We're going to go to infinity. What about the other infinite terms I didn't add? How close are we? Well, we've only done 6. Are we pretty close? You would think we're not very close at 6. We'll find the remainder of the error. So the difference between the actual sum and the sum of our 6 terms, so that's how you would write it, the actual sum in R6 is going to be less or equal to the next term. Well, what's the next term? Would be the 7th term. The 7th term would be a positive 1 over 5040. That would actually be, that's how accurate we are. Now in decimal, I did that decimal, it was, let's write it right below here. 0.00198. As far as 3 decimal accuracy, we're 0 away. So we're pretty close. That's a pretty good answer right there. We're close. Look how close we are. That's the farthest we are is 0.000198. So if someone said, is that the sum? I'd say pretty much that's it. So rounded to 3, 632 is the sum of the infinite series, okay? Now, since the next term is add, it doesn't matter if it's add or minus because they said the absolute value, the distance, okay? Since the next term is add, then we're a little below the actual sum because we're going to add the next term, so it's somewhere above us. So that's actually a under approximation a little bit. So the next number is actually, this is just bonus information here. The actual sum is a little bit greater than our 631,944, but it's no more than adding that to that. It's no more than that distance, which I did. And I got 632,143. This is just, we don't need to write that down. That's just bonus information. But I know the sum's somewhere in that little range because this is what I got, and that's the error. So I know it's somewhere between those two because the next term I would add. Okay? So that's kind of the error that you find. Now there's something we're going to learn that's a little more powerful, Lagrange error bound. That's coming up, and it looks very similar to this. It has some slight little changes. It's a little bit more difficult. Okay? So that's the alternating series remainder. Now I told you I'm going to show you why this works. Okay? So let me go back to this sum so you can see. Let me erase this error here. Just give me a little space. So let's think about what this means. So you start off with adding 1. So we'll call that distance 1. Okay? Then you take away a half. So then you go back to here, halfway. But then you add a 1/6. Okay? So you're going to add a little bit more. Well, then you're going to take away 1/24. So you're going to go 1/24. And then you're going to add 1/20. So it's a little tiny bit. Then you can see how you're getting narrowed down the answer. The sum is, you're only adding 1/20. You're adding these are such tiny numbers that you're adding, subtracting. So you've already got the sum pretty much narrowed down about right here. We're pretty close. And then these are little adjustments and stuff, slight adjustments over time. So it's kind of like when somebody says, hey, high or low, pick a number, and you say higher than that. No, pick a number between 0 and 50. You would say 25 to cut the answers in half. That would be a smart guess. It'd be dumb to go 49 lower, 48 lower. I mean, you're an idiot. So 25, and if they said higher, then you've cut the answers in half. Okay, and that's kind of the idea. So this is what's happening to the series is we're just going back and forth and we're narrowing it down. So that's why we can be pretty accurate. Okay, so that's the alternating series remainder.